Thank you for having me. So I'm talking today about the Rust compiler, and I'm just giving a broad overview to explain basics of how it works and some of the things that go on inside it. There we go. So I'm a member of FutureWay's Rust team. I've been contributing to the Rust compiler since 2016. I'm a member of the Rust compiler. I'm a Rust compiler team contributor and a member of several working groups. And I've also worked on several other compilers, including SpiderMonkey, which is the JavaScript compiler inside Firefox. And I've worked on Valgrind and a couple of other research compilers in academia. So I'll start with a high-level overview about the compiler. So when you install Rust on your computer, you get a tool chain, and that tool chain has several pieces. And the first piece is the compiler itself, which is called rustc. And it's the program that's responsible for translating your Rust source code into executable machine code. But you usually don't actually run rustc directly yourself. You instead run Cargo. And Cargo is a build tool and package manager. And you normally run commands like cargo build and cargo test. And then the Cargo itself will then invoke rustc on your behalf. There are also a couple of other pieces in the toolchain, including the standard library, which most Rust programs use, and also rustup, which is the installer program that will update your compiler when a new one comes out, and various other tasks like that. So we use a release system that's based on something called the train model. So one way that you might release software is, say, every year you do one big new release. And if you do that, then that big new release is exciting and there'll be lots of new features in it. And that's really good from a publicity point of view. But it has some downsides as well. And those downsides are that if, as a compiler developer, if I write something new, it might take up to a year before it gets released and reaches Rust users. And also, if I might be tempted to, if I'm getting close to like the deadline for a release, you might try and rush a feature in because you don't want to have to wait a whole another year. And so instead we take a very different approach. We have one release every 6 weeks. So you get sort of 8 or 9 per year. The current version is 1.81, although I think today might be 1.82 might be coming out. So the good thing about this, releases are frequent, they're predictable, there's no need to rush new features. One consequence of this is that some releases have big changes that are exciting, but some don't. Some of the releases just have small incremental improvements. And so overall, this is good from an engineering point of view, but it's maybe not so good from a marketing point of view, but that's okay. So the compiler supports a lot of different platforms, and this platform support is in 3 different tiers or groups. So tier 1 is the highest level of support. These are platforms where we are guaranteed the compiler will work. We provide official binaries, and there are 9 platforms. This includes x86-64 for Linux, Windows, and Mac, 32-bit x86 for Linux and Windows, 64-bit ARM for Linux and Mac. And then the next tier is tier 2, where it's guaranteed that the compiler will build, but it's not actually guaranteed that it will work 100% correctly because we don't run tests. And there are more than 80 platforms in this category. And then finally, we have tier 3, where there are basically no guarantees. It's not guaranteed to even build, let alone work. Hopefully it will, but we don't check that. And there are more than 170 platforms in this category. The license is fairly straightforward. It's a dual MIT Apache 2.0 license. This is an open source license. It's very flexible. It imposes very few restrictions on users of the code. And it's a license combination that is used for a lot of different Rust projects. So for the teams that work on the compiler, it's basically in 2 pieces. There's the compiler team, which has 14 members, and they're responsible for developing and managing the compiler's design and code. And then there's a sort of a secondary team called the compiler team contributors, and that's another 35 members. And these are people who are regular contributors to the compiler. So combined, that's almost 50 people. And everyone in these teams is able to approve changes, so they have review permissions. But you don't have to be a member of one of these teams to contribute to the compiler. Anybody can contribute. And the way you can contribute is through the following workflow. So it's all based around GitHub. We have the code repository is on GitHub at github.com/rustlang/rust. All changes are made as GitHub pull requests. All changes require a review from a team member, so one of the people mentioned on the previous slide. All changes must pass CI testing before being merged. And then also all bugs and problems are reported via GitHub issues. So it's a fairly straightforward, standard GitHub-based workflow. It tends to work pretty well, and there's nothing too complicated there. I'll now talk a little bit about the internals of the compiler. So rustc is written in Rust. For people who are familiar with compilers, this slide is going to make a lot of sense. For people who are less experienced with the compilers, this slide may be a little confusing, but I'll do my best to explain it. So there's this process called bootstrapping, and the idea is that if the Rust compiler is written in Rust, so how do you get it to, how do you get a working compiler? And the idea is that if you have version n of the compiler and you want to compile it, you use version n-1, which was previously compiled, in order to compile it. How was version n-1 compiled? Well, that was compiled with version n-2. And this goes back all the way through a long chain of history over several years. And in fact, the original Rust compiler was written in OCaml, because before there was a Rust compiler, there was nothing with which you could compile Rust. So you have to write it in a different language. And this is very standard compiler technique. And then the next thing, which is when it gets really confusing, is that once you've compiled version n with version n-1, you now have a working Rust compiler, and you can then recompile version n's code with the version n compiler, and it's a compiler that has compiled itself. And this is what we actually release. And so if you're running the Rust compiler, you are using a compiler that is built in this way, and this is called a self-hosted compiler. So if you haven't heard of this technique before, it's a bit strange and it takes some practice to get your head around, but it's actually a very common way of doing things. In terms of the amount of code in the compiler, this slide shows you the output of a program called toke, which measures the number of lines of code in a program. And you can see there's a lot of stuff at the top. In different languages, there are small numbers of files and small numbers of lines. But if you look towards the bottom, there's a line with Rust code, and I've highlighted one number there, which is 667,398, which was the number of lines of Rust code in the compiler as of a few days ago when I wrote this slide. So this is a fairly large number. It's not enormous, but it's also not small. And then if you actually get the code for the compiler, there's a directory in the repository called compiler, and if you change into that directory with cd compiler and then type ls, this is what you see. There are 72 different crates within the compiler, and they're fairly well logically named. So there's a lot in this slide, and I will return to this slide several times, so you don't worry about being overwhelmed with this information. But I've highlighted a few things that even at first glance might you have some idea of what's going on here. So in the first column on the left, you can see, if you can see it, if I'm not standing in your way, there's a crate called rustc borrow check, which is the implementation of the Rust borrow checker, which you may have heard of. Further down, we have rustc codegen SSA. So this is to do with code generation, and SSA is short for static single assignment, which is a particular compiler internal representation form that is often used. Then if you look at the third column, I've highlighted rustc lexer and rustc parse, and these are two crates that are involved with lexing and parsing the code, which is an early step in compilation. So the names of the crates are generally quite logical. And I'll talk about code representation. So this is very important with compilers, is there's often multiple ways in which code is represented. And typically, in a typical compiler, you won't just have a single representation for code, you will have multiple, and you'll pass through them as you go along in a kind of a pipeline. And again, this slide has a lot on it, and I'll step through it a piece at a time, so don't worry if it doesn't all make sense at the moment. So let's just focus on the first bit and the last bit. Obviously, you start with Rust source code, it goes into the compiler, a bunch of stuff happens, and then you end up with executable code. So those first steps are lexing and parsing, which I already mentioned. So when you take this Rust source code, you pass it through a lexer, and that breaks the text into individual sort of atomic, smallest possible units of Rust code. These are things like identifiers, punctuation, string literals, numbers, and so on. And that gives you a stream of tokens, and then that token stream gets parsed, and we end up with something called the AST, the abstract syntax tree, which is a tree representation of the code. It's a very faithful representation of the original Rust code. It's very close to that original source text. And while we're at the AST level, we do a number of things, including macro expansion. So both declarative macros and procedural macros get expanded at this point. And we also do name resolution. Now the next step is we take the abstract syntax tree, the AST, and we lower it into something called HIR, which is short for high-level intermediate representation. This is a slightly lower level representation. It's a little bit further away from the original Rust code. We've thrown away some of the details. And this is an important point because this is where we do type checking and type inference and also trait solving, which are all very important parts of the compiler's operations. After that, there's a second lowering step to something called typed here. And we do a few more checks there, checking that your program is not breaking the rules. After that, we then lower one more time to something called the mid-level intermediate representation, or MIR. This is a much lower level representation. It's kind of a control flow graph form for people who know what that is. You have basic blocks, which are sort of chunks of straight line code, and then you have jumps between them, and you're quite some distance at this point away from the original Rust code. And at this level, we do several more important things, including borrow checking, various kinds of optimization, such as constant propagation, copy propagation, dead store elimination, and inlining. And this is also where monomorphization happens, which is when if you have a generic function that needs to be instantiated for several specific concrete types, this is where that happens. And so that generic function will be duplicated for each of the relevant types. And then finally, we have one more translation step, which you could call the first code generation step, and we translate MIR into LLVM IR. So LLVM is a separate program and a separate project, and it's a sort of a code generation framework, and it's very good. It produces very high quality code. It has a lot of optimizations built into it, so we take advantage of that. And so LLVM gets sort of packaged and incorporated into the Rust compiler, and so we translate our MIR into the form that it takes. It does a lot more optimizations and generates the executable code that you actually then run. Okay, so now we have sort of the full picture of all the different levels. So we start with the Rust source code, we end up with the executable code. We've got 5 different representations within the Rust compiler. We've then got one additional representation for LLVM, and we've got all the various steps between them, such as lexing and parsing, lowering, and so on. Now, if we return to this listing of all the different crates, some of this is going to make more sense now. In the first column, you can see there are 5 different crates with AST in the name, and so these all relate to the abstract syntax tree. A little further down, you can see there's a crate called rustc cogen LLVM, so which is related to LLVM. In the second column, you can see 4 crates related to here. In the third column, you can see another LLVM crate, and then 3 crates that are related to MIR. So this listing is now starting to make more sense, and it's more clear where different things belong. Another interesting point that's worth noting is there are some sort of memory management techniques that are used within the compiler. One is called interning, and the idea here is that sometimes you have a particular value that might show up in your program lots of times. You might have an identifier, the name of a function, and that might show up dozens or even hundreds of times in your program. And if you represented that identifier as a string in memory hundreds of times, that would take up quite a lot of space. And so you want to avoid that, and you want to only represent that once if you can. And so there's a process called interning where you do that every time you see a new value. You actually check, have I seen this one before? You have to look up in the table. And if you've seen it before, then you just sort of have a pointer to it basically instead of storing it again. So this saves a lot of memory and also means you can do cheap equality comparisons, but it does mean that creating a new value does take a little bit more time. The compiler also uses arenas, which is a memory allocation technique where basically you have a chunk of memory from which you can allocate lots of objects one at a time, and then you can free them all at once in a single operation. Another thing of note is that we have something called queries. So in a traditional compiler, you have multiple fixed passes, and it's a very sort of rigid pipeline of operations. Rust-C is a little more flexible. We have these function-like queries that compute various kinds of information. So like one example of a query is called type of, and it computes the type of something. And these queries are memoized, which means that they're computed once, and then if you need them again, they're stored in a table. So if you need to compute the type of a function, it'll do it once, and then if you repeat that operation again, it'll say, oh, I've already seen that. I've got that stored in a table. I don't need to recompute it. And this is then the basis for incremental compilation, because this sort of table of stored values you can actually save to disk, and then the next time you recompile, you might find that things that haven't changed, you can look it up in this sort of little, almost like a database of values, and you can save a lot of time if not much has changed. Now returning again to our source code, you can see in the first column, we've got a crate called Rust-C Arena, which relates to the arena allocation that I just mentioned. And then in the fourth column, you can see two crates with query in their name that relate to the queries that I just talked about. Another topic of interest is parallel execution. So there's a couple of different ways that parallel execution happen. So one is inter-process parallelization. So this is where you have more than one Rust-C process running at a time. And this is managed by cargo. So I've got here the output of a profiler. So if you run the command cargo build -- timings, it will produce this nice graph that sort of gives you a visualization of how your project is compiled. And so in this picture, each line represents a single crate being compiled, and on the horizontal axis we have time. And you can see there are like 31 crates being compiled in this graph, and the first 26 or so of them all start compiling at the same time, and they all compile in parallel. And so this is on a machine that has a large number of cores and is able to compile 20 plus things at once. And then you can see at the bottom, some of these ones start a little later. So maybe it's because there weren't enough cores, or maybe it's because there are dependencies and you just can't compile a certain crate until the previous one has finished compiling. And now this shows a later stage of compiling this same project. So we've got another 30 odd crates here, and you can see this is getting towards the end of compilation. There's a lot more dependencies between different crates. And so again, we're in the situation where some of these crates, we have to finish compiling crate A before we can start compiling crate B that depends on it. And so we have a lot less parallel execution towards the end. In particular, near the end, it becomes almost serial. We're only compiling one crate at a time. And so this sort of cargo level inter-process parallel execution is quite effective early on, but it gets a little less effective later on. And so we want to have some more parallel execution in other places. And so here we have the intra-process parallel execution, so within a single Rust-C process. And there are two kind of areas for this. One is that in code generation done by LLVM, it's able to break code into multiple chunks and run one thread per chunk and do the code generation that way. And then also there is some, under development, there is some parallelism being added to the front end, although this is still experimental and has not actually been turned on yet. And so I've got here another diagram. So this is the output of a profiler called Samply. And each of these lines, horizontal lines, represents a different thread of execution. And you can sort of see there's two halves. I've added a red line, a vertical red line in the middle, and to the left of that line is the front end, and to the right of that line is the back end. And you can see at the very bottom we have the main thread, and in the front end, the main thread is doing all the work. And then once we get to the back end, then we have LLVM firing up a number of threads, and those are working. And there's a decent amount of parallel execution going on there. And so obviously it would be nice if the front end could have more parallel execution so that the width of this graph will get smaller and the compile times will get faster. Another topic of interest is error messages. So the Rust compiler is famous for having good error messages. A lot of effort goes into this. Like, a lot of people spend a lot of time on this, and a lot of new contributors get into the project by improving error messages is like some of the first work that they do. So this is a good entry point. And good error messages are important because Rust is not an easy language to learn. And so if you have good error messages, that can be a really valuable education way of teaching people. So here's an example of a compile error. This is one error. We've got several, quite a few lines here. We've got the first line tells you a short version of what's going wrong. The second line tells you where the problem is. The next few lines have a little excerpt of the code and some little markers that show you, oh, this is where the problem points are. And then it even ends at the bottom with some help where it actually gives you suggestions saying, well, this is how maybe you could change your code to fix the problem. So it's a very comprehensive and sophisticated error and very, very helpful. And related to this is translation of errors is a topic of interest. Error messages are currently only in English. There is a long-term project underway to provide translations to other languages. It's not easy, particularly because there are so many error messages and they are so sophisticated. It makes the translation job difficult. But this will be a thing that will make Rust easier to use for many people and is a worthwhile thing. So once more, returning to the source code, we can see in the first column we have a crate called baked ICU data, and in the second one we have one called fluent macro. So ICU and fluent are two different libraries that are related to translation between languages. And then also in the second column you can see there are three crates that have error in the name, and they're all related to error messages. So there are also several backends. So this is about different ways of generating the code. So I talked previously about LLVM, which is the production backend that we use. There are also two other sort of more experimental backends that are available. One is called CraneLift. I think Amanyo talked about that earlier. It's under development, but it is quite usable at this point. The motivation here is you have faster compile times for debug builds. That the quality of the code produced by CraneLift is maybe not quite as high as LLVM, but it will produce that code more quickly, and particularly for debug builds, this might be a trade-off that is good for a lot of people. And then for GCC is the other backend. So GCC is a well-known compiler. The motivation here is it supports a lot of platforms, including some quite sort of niche embedded in platforms that LLVM does not support. And so that's why that's of interest. Once more, returning to the source code, each of those backends has a crate: CraneLift, GCC, and LLVM. A few other matters. So testing, there are a lot of tests broken into several test suites, and these cover errors, code gen, debug info, a whole lot of different forms. There are more than 22,000 test files, and there's more than 600,000 lines of code. So you might remember that slide I showed earlier about the number of lines of code. We had 667,000 lines of code in the compiler, and then we have a similar number of lines of tests. So almost as much test code as there is actual compiler code. Performance is also important. We care deeply about compile times. We want them to be as fast as possible. So we have a benchmark suite called rustc perf. It has about 45 benchmarks in it that represent sort of a wide variety of different styles of Rust code. This benchmark suite gets run on every merge. So every change that goes in, we run the benchmark suite, and the results from that are automatically posted to the relevant GitHub pull request. And so the author of that pull request will be told whether or not their change had an impact on compiler speed. Perhaps you improved it, perhaps it was a regression, or perhaps it was neutral. And if it isn't a regression, then maybe they can consider reverting the change, or they could perhaps try to investigate and see if they could win that speed back. Rust cperf also has a website with some detailed performance history that you can look into. Another interesting topic has to do with breaking changes. So Rust has strong backwards compatibility guarantees. Like if your code compiles today, it should compile 5 years from now, 10 years from now, and so on. Very, very occasionally, we need to break that because of either bugs in the compiler or bugs in the language. And so it's possible that you might have code that compiles today but doesn't compile in the future because of one of these fixes. And so if we have one of these fixes, which are rare, but they do happen occasionally, we want to have some idea of, well, is this actually going to break a lot of code in the real world? Or is it some very obscure edge case that doesn't actually tend to show up in real code? And so there's a tool called Crater, and you can request a change be run through Crater, and what happens is that it will, in the cloud, it will compile every crate that's on crates.io with your change compiler. And this is over 150,000 crates. And this takes a couple of days, and then you get a report back that tells you whether or not your change broke any code. And if you're lucky, maybe it didn't, and so you can make this change without any worries. Occasionally, you might find that it breaks a certain number of real crates, and like we're reluctant to make that change straight up. And so what we might do is start issuing a warning and say, this code currently compiles, but it shouldn't, and in the future it may stop. So you might want to make a relevant change. And when this happens, you might have these warnings in place for months or perhaps even a couple of years, and then eventually they'll be converted to a hard error, and that code will stop compiling in order to fix the relevant bug in the language or the compiler. There are a few other tools that share code with the compiler. One is RustDoc, which is the tool that generates documentation from doc comments. Another one is Miri, which is the Mir interpreter. The idea of Miri is that it can detect bugs in unsafe code at runtime. So if you're writing unsafe Rust code and you want to have some level of checking that you're doing reasonable things, Miri can be useful. And then finally, Clippy is a linting tool that has a lot of different lints, and it also shares a lot of code with the compiler. So to finish up, so Rust C, it's a large and complex and sophisticated compiler, and yet, at least I find it's relatively easy and very enjoyable to work on. And I think the reason for this is that Rust itself is just a really great language for writing compilers in. The speed, the safety, the control, and the expressiveness all make it a very pleasant experience. And if you're interested in contributing to the compiler, there is a guide called the Rust C Dev Guide, which is available at this URL. And it has a lot of details, goes into a lot more detail than what I've talked about today about all different aspects of the compiler's internals. It's a very good starting point for anybody who is interested in contributing to the compiler. And that's the end of my talk. Thank you very much.